Okay, so last week we started a new section dedicated to proving some new criteria for excluding fusion ring from categorification. So this new criteria, so in fact this section do not need the use of triangular prism equation. This section is involve only the Pentagon equation. So what's the point of this section in this course, in this paper, is that in fact the main application of the paper is on the classification of unitary simple integral one Frobenius fusion category. And as I explained before, we had a classification of such a fusion ring for with a certain bound, and most of them was excluded from unitary categorification using quantum Fourier analysis, except two for a given bound. And these two, the hardest one was excluded using triangular prism equation localization strategy we already explained before. But there remains another one which can be excluded by the zero spectrum criterion. So the zero spectrum criterion is, this section is in some sense independent of the triangular prism equation. But for completeness, we will talk about that. Then we will have a complete proof of the classification of what I said, unitary simple integral one Frobenius fusion category, up to a certain bound I explained in introduction. So, so what is spectrum? So we fix, as I explained last week, we fix a generic Pentagon equation like that, and we define its spectrum to be the set of I0 for which the right-hand side is non-zero. More precisely, it is defined here. So the right-hand side is, as I explained, I will not go into the details I explained last week, but yeah, according to that, you see that this right-hand side is non-zero if and only if these three fusion coefficients are positive. And so we will state and prove two criterion. One, where the cardinal of the spectrum is zero, called the zero spectrum criterion, and one when the cardinal is one. And more precisely, for this one, we will reformulate the existence of an equation of this form, xy equals 0 with x and y different from 0. We will reformulate the existence of such an equation, such a Pentagon equation. And for the one, it's of this form. 0 equals xyz with xyz different from 0. So, so we will now state the first. You will better understand what I mean by that. To prove this criterion, we will use this one-dimensional trick. So you pick for non-zero morphism if one of these three sum are equal to 1, then this F symbol is non-zero. So this statement says that we have a way, a priori, we don't know if this F symbol is 0 or not. But this assumption, this one or this one or this one, force this F symbol to be non-zero. So we will first prove this lemma, and then we can state the zero spectrum criterion and prove it, and then we will state the one spectrum criterion and prove it. And then we will apply this criterion to exclude what we call F660 from any categorification. And that will be the last step for the proof of our classification of unitary fusion category I mentioned. Okay, so how to do that? How to prove this lemma? So recall from this notation. So we mentioned this is the basis of this Hom space, and recall this notation alpha prime correspond to the dual basis in this Hom space given by the binaire form we mentioned at the beginning of the course. Okay, up to some natural adjunction isomorphism, but anyway. So the prime correspond to the dual basis. Okay, so here we have four morphisms in some basis, and we will consider, in fact, this prime and this prime. So in the dual basis. So take, wait, that should be there. Take mu, so the element in the dual basis, so the dual of so mu3 prime, mu4 prime, from notation like that. Then by composing, by making a proper composition, an appropriate composition, we can. So let me. Then, as done pictorially, I will copy and paste the picture to explain what I mean. In section 13. So where is this picture? Oops, after that. No. Wait. Oh. It's in section 12. Section 12. Okay. I will find it quickly. Yeah. Quite close. So which one am I talking about? This one, okay. Yeah, this one. So we will no more consider this kind of tilde because we don't, as I said, we don't need to reformulate everything in terms of such form. But in fact, algebraically, this picture corresponds to what we want algebraically. So let me just copy and paste this picture. And then I will need to explain more. Yeah. Oh, too much. Like that should be okay. What happened? Why I have only that? I don't understand. Okay. Quite complicated. So I'm sorry. Let me, maybe I will just copy from the paper. It will be easier. Here. Okay. Section 12. Yeah, this one. You take this one. Okay. I will copy and paste this one very quickly, and it will be okay. Tac. Okay. Tac. Okay. Okay. So this is what we already proved in section 12. So let me write it like that. Section 12. Okay. So now we will reformulate this algebraically, but we will no more consider the tilde. So as follow, you have so mu2. So let me take the blue color. Okay, so mu2, mu1, tensor identity of I4, composed with identity of I1 tensor mu3 prime, composed with mu4 prime equal to, so I1, I2, I3, I4, I5, I6. Okay, mu1, mu2 times mu4, composed with identity of I1 tensor mu3, identity of I1 tensor mu3 prime, mu4 prime. Okay. So it's, you should convince yourself that these two things are the same. But this is just a picture of that. This and these are the same thing. So forget about the tilde, in fact, because the tilde is just something just for the shape. But okay, so this is okay. So what we want to prove in this lemma is this F symbol to be non-zero, but this F symbol appear here. So to prove that this is non-zero, it is enough to prove that this is non-zero. If you prove that this is non-zero, then this constant cannot be zero. Okay. So to show that this is non-zero, okay. It is enough to show that so the left-hand side is non-zero. Okay. Okay. So the proof will be, as I said, the proof is not complicated, but it's a bit longer. In fact, we have three conditions. This one, and this one. These three conditions correspond to dimension of some space. So this corresponds to the dimension of some space I will explain. And this condition say that it is of dimension 1. Same, some space is dimension 1 and some other space is dimension 1. This space will be involved. So what will be the idea of the proof is that okay. We will consider, for example, this part. This morphism is in the space of which is one-dimensional by the first condition. And so, but the dual of this one, or something close to the dual of this one, is also in the same one-dimensional space. So this one and the dual of this one, or something close to that, are in the same one-dimensional space, and they are non-zero, so they differ from just a non-zero constant. So you can replace that by the dual of that, and so it's non-zero. Because by the definition of duality, if you compose by the dual, etc., we take the appropriate trace, etc., it's non-zero. So we will explain that. So this corresponds to the first condition. The second condition will involve this part, and the third condition will involve this part. Okay. So let me write. So the sum stated in the assumption correspond to the dimension of space. Okay. Corresponding to of 3 space. 3 space. Containing 3 components of above morphism. So you have the first up to, yeah, I have to say it's up to natural adjunction isomorphism. Up to. I will explain in more details, no, don't worry. Up to natural adjunction isomorphism. In fact, we said up to natural adjunction isomorphism because we wanted to have something very symmetric where we wanted to have the K at the same place everywhere. Otherwise, we don't need to say, you can reformulate that in such a way we don't need to say up to natural adjunction isomorphism, but then you don't have the symmetry of the K. So, as I said, the first point corresponds to that. Point 1. This one. Point 2. So by 1, 2, 3, I mean that 1, 2, 3. Okay. And the last one is like that. That's the full thing. Point 3. Okay. 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 So, 1. For the details. So as I said, it's up to natural adjunction isomorphism. So if the sum for K n I1, I2, K n K I4, I5. So remark that we move a bit the K because it's more appropriate for the proof. Here the K was there. So we just apply the formulus reciprocity here. So we move the K. So this corresponds to the natural adjunction isomorphism. Okay, so if this is equal to 1, then I will write the Hom space of dimension 1, then corresponding Hom space xi1 tensor xi2 tensor xi4 to xi5 is one dimensional. So why that? Why this corresponds to this Hom space? So you are making the tensor product I1, I2, I4. So xi1, xi2 decompose as xk. So this is a sum. This is how to say, direct sum of m I1, I2, k of dimension tensor xk. So this is the dimension of this multiplicity space is exactly that by definition. So you have a sum of ik, a sum of xk. So you make the product with that. So you have the product of k and I4. And then the Hom space of xk tensor xi4, xi5, this dimension, the dimension of its Hom space is exactly that. So if you, in summary, the dimension of that is exactly this sum. Okay, so this is one by assumption. Okay, now we want to consider, we will consider this morphism. We will say that this morphism in this space, but also another morphism we are interested in will be in this space. So they differ only by a multiplicative constant. They are both non-zero. So, but mu2, mu composed with mu1 tensor identity of I4 and mu4 identity of I1 tensor mu3 are non-zero morphism in this space. Okay, so let me write the picture for these two morphism. So you have something like that. And here you have something like that. Okay. And like that. And the morphism are written here. So mu1 is here, mu2 is here, mu3, mu4. And the object indices are which color? This color. I1, I2. Anyway, we don't really need the object here, I5. So they are in the same home space from I1, I2, I4 to I5. So you have these two morphisms. I state that they are non-zero. Exercise. Exercise. So it's an exercise to show that they are non-zero. So the hint of the exercise is to consider Schur lemma and reform and write mu, the morphism mu. So by mu star I mean mu1, mu2, mu1, mu2, mu3, mu4. Or I should say mu I then. Mu I as a vector with non-zero entry. So what I mean by that? Okay. So you have mu1 is from mu1 is a morphism from xi1 tensor xi2 to x, I don't remember in fact, k, I guess. Say xk. xi1 tensor xi2 xk. No, not xk. So something. So xi1 tensor xi2 decompose, as I said, the sum of mi1, i2, k tensor xk. And then you go to this object, I don't remember, I. So this morphism can be written as a vector with some non-zero entry. Not all the entry are zero, but for each component, so with some non-zero entry. So you have mu, for example, mu1 is in the home space of xi1 tensor xi2 to x so mu2, where is mu2? Xi something, I forgot the indices. So, but xi1 tensor xi2 is the sum of mi1, i2, k tensor xk. So, so you have, in fact, this Ohm's Bayeshur lemma. If xk, if k is different from this I, then Bayeshur lemma, it is 0. So you have 0 entry. And when k is equal to that, so this happens this many times, the dimension of that, it's an isomorphism. So it's a non-zero entry. So there are non-zero entry. The entry are non-zero when this k is equal, this indice is equal to that. So you can realize each morphism like that as a vector with non-zero entry, corresponding to the morphism from xk to xi something. Each of these morphism, so it's okay. So mu is supposed to be non-zero. So there must be non-zero entry, like that. Okay, so you have this non-zero entry here. Here also. And then you compose, you get something which is non-zero. So it's, yeah, you have to complete the exercise like that. You have something non-zero here. You take the entry which is non-zero here, and you compose with this one. Again, you get something non-zero, etc. Okay. So these two morphisms are non-zero. And this is very important because this is the point of the proof of the lemma. You want to prove something is non-zero. We assumed this Hom space is one-dimensional. We pick two morphisms in this Hom space which are non-zero. So one is equal to the other up to a multiplicative constant. And then we will be able to replace this part by this part up to a multiplicative constant. But this part is a dual of this part, so their composition cannot be zero. And so this is non-zero. And this will be the proof of this lemma for the point 1. And then we will do the same for point 2 and point 3. Okay. So they are non-zero. So mu2, mu1 tensor ID of I4 equal lambda by non-zero and one-dimensionality. 3 for some non-zero constant scalar. Therefore, as I said, we can replace one by the other in the what we are interested in. So this one. So let me copy this one. So this is equal to. So we replace which part? This part. So lambda mu for identity I1 tensor mu3 composed with identity I1 mu3 prime mu4 prime, but this is non-zero. This is non-zero by duality. By duality. By definition of duality, see the section 3. As I said, this is a dual of that. So their composition is non-zero. Remember, you have the duality is defined involving the Kronecker symbol. So when you have the dual basis and when you have the appropriate dual like that, this is 1 and otherwise it's 0. So here it's non-zero. And this is non-zero, so this is non-zero. Okay. So in fact, the two other points will be the same ID. The third point will be a little bit more complicated, but this is the same ID. The ID is not so complicated, in fact, but the way to write it is a little bit long. Yeah, it's straightforward but long. Same idea everywhere. You consider you consider a home space. By assumption, it is one-dimensional. Then you pick two morphisms we are interested in. So we will do the same for this part. We did for that. We will do the same for this part and then for this part. And so we will, yeah. Okay, so second part. If the sum over k n I1, I6, k, n I3, I4, k is equal to 1, then the home space xi1 tensor xi6 to xi3 tensor xi4 is one-dimensional. One-dimensional. So remember that in so this is not the one in the statement we have something like that. But we restated. So what is the point of writing? I'm not sure. I'm not sure we really need to write it this way. So this is a little bit different. The k are in the same place, but you see here is I1 star, I3, I6, I4 star. Whereas here it's I1, I6, I3, I4. So I don't understand the point of changing this. Let me write 9.2 I1, I6, K, N, I3, K, for the statement. Anyway, they are the same. The dimension is the same because the home space, the corresponding home space, are isomorphic. The home space corresponding to what is written in the statement is the following. X I6 tensor xi4 star to x1 star tensor xi3. So natural adjunction, there is a natural adjunction isomorphism. This is not complicated. You have you move this one on the left, and so you get that, and you move this one on the right. So you get exactly this home space. So they are same dimension. So as I said, the dimension of that is what is written in the statement of the lemma. The dimension of that is exactly that. Okay. So you can see it here. So here it's easier. I1, I6, I3, I4. So you are making the sum over K. Here you have a decomposition over xk, decomposition over xk prime. But this is non-zero if k equal k prime. So you can take the same k, and then you just take the sum, etc. So that's okay. Okay. So now the same idea. We want to pick two morphisms, but this morphism ID1 tensor mu3 prime and mu2 prime mu4 are non-zero for the same reason as before, the exercise before, are non-zero morphism in this home space. So here, what was the color I used? Okay. Here, this is equal to something like that. This is equal to something like that. So here, the morphism, so mu1, mu3 prime, and here mu4, mu2 prime. So for this, with the same idea as the exercise before, these two morphisms, so you reduce to consider vector with non-zero entry, and you see that you get something with non-zero entry here and here. So they are both non-zero home space. So, and I will write this the end of the statement before the pause. So mu, so this one. So this equal lambda this for some non-zero lambda. Non-zero lambda scalar. Okay. So I will finish the point before the pause. Therefore, you have this again. Equal lambda, and now you will replace the part in the middle. So mu2 prime, mu4 prime, which is non-zero by duality as before. So we don't need parentheses. By duality. Because yeah. Now, here the duality is even immediate. These two are a couple of dual morphism. Okay, now, so after the pause, we will consider the point 3, which is a little bit more complicated. Pause. 9, 2. Okay, pause. So we restart. So point 3 now. So the point 3, as I said, will be a little bit more tricky. It will involve this part, but in fact, we will first need to reformulate a bit this part up to zigzag relations. So this proof was written several years ago. I don't remember if this is really required to make such complicated proof, but at least this is interesting that we need to apply such zigzag relation for such a proof. So, okay. So now, if some n I3 I2 star k n k I6 I5 equal 1, which is exactly as before, but I guess up to natural isomorphism here. We apply the Schur. So we move this and this and remove. So it's okay. So this is the dimension of the Hom space. The Hom space xi5, xi3, xi2 star, xi6. Okay, is one dimension. Now, okay, so now we need to do something a little bit more complicated. But so it's not clear to me that we really need that. But mu1 tensor ID I2 star ID I1 tensor, and here this is the notation for this section. The co-evaluation map is written like that, cup and cap. But yeah, tensor ID I6 composed with this. So this is so let me write the picture for that. This is equal to this picture. So you have one thing like that, one, so the co-evaluation map, and then something like that, and like that. So you see mu 4 prime. So you start by mu 4 prime, and then you compose. You have identity of I6 and this part, which correspond to this part. So this part, you start by that. So you have co-evaluation map identity, and then you have mu1 identity. So it's okay. Mu1. And I don't write, but this is a co-evaluation map here. So this is non-zero. So for the same reason as before, I5, I3, I2 star, I6. This one and another one, and so okay, so let me write it first, the picture for the other one. It will be like that. So like that. Then this here. And like that. Okay. So here we will consider this mu2 prime. And here it will be mu3. And in fact, this, oh wait, let me write the object also. So I3, I2 star, I6, I5. So this part will be used several times. So we will give it a name. This will be the dual of zeta. And we will use zeta and zeta prime several times. So that's why we give it a symbol. So this is, in fact, so identity of I3 tensor zeta prime composed with mu2 prime. So you have mu2 prime here, identity of I3 here and zeta prime here. So these two pictures, so for the same reason as before, involving some non-zero entry in some vectorial representation of the morphism, these two morphisms are non-zero. So they are non-zero. Are non-zero morphism in the home space, this home space, I5 to I3, I2 star, I6. Are non-zero morphism in this home space of one-dimensional home space. Okay. And okay, so where, in fact, you can write zeta directly as follow. I2 star, tensor identity. So this is evaluation map, tensor identity of I4 composed with identity of I2 star, tensor mu3 prime, which is just the rotation. You just rotate this part like that. So you get something like that. Cool. Like that. I2 from I2 I2 star I6 to I4, and the morphism involved in the middle is mu3 prime. Okay, so okay, this is also non-zero. This zeta is also non-zero. Is also non-zero. Okay. And zeta. So the notation I will not repeat. This notation prime is as the notation we mentioned before. So done. Equal to multiplicative constant. So this equal this times this with lambda non-zero. For some non-zero lambda. Therefore, so now we want to, okay. So we are not completely done because what we have here, so which one? What we consider here is not exactly this part. Is not exactly this part. We need to apply, we need a pictorial proof of that involving zigzag relation. Therefore, so let me write again. So this, yes, this one. P. This is equal to So mu2 ID I3 tensor zeta or mu1 ID I2 star ID I1 tensor co-evaluation map 2 tensor ID I6 and mu. So it will be much more clear with picture. By picture. But maybe I should. So this the picture for that. So you have the left-hand side is proof by picture. The left-hand side is like that. And in fact, this left-hand side is exactly what we want to prove it is non-zero. Is equal. So let me write the morphism mu 4 prime mu 3 prime mu 1 mu 2. And this by zigzag relation is equal to the right hand side having the following picture. So that, and then you have an evaluation map, co-evaluation map, something like that. Identity here. So something like that. It's a little bit complicated, but like so mu and the same, in fact, the same morphism are involved. Mu2, mu4 prime, mu1, and mu3 prime. And the zigzag relation. So you apply. Hello. Hello. Apply the zigzag relation. So this part equal this part. So you can replace. So this picture equal to this picture. So now let me explain a little bit why these two pictures. So mu4 is here, and then you have identity mu3 prime, and then you have mu1 identity 2. That's okay. Now mu4 prime, same thing. And then identity I6. Then you have co-evaluation map identity corresponding to that, and mu1 identity. And then you composed with Z. So identity 3 And here you have the zeta, which is written here. This part corresponds to this part. I'm not mistaken. Okay. So it's okay. You have, it's clear that these two pictures correspond to this formula. But it's also clear that these two pictures are the same up to zigzag relation. So these two formula, these two are equal. But now we can apply what we proved before. This is equal to that. But this appears here. Okay. So we can replace that by that. And then what we get here is exactly the dual of that. We are done. So this is equal to, let me just put this like that. Okay. This is equal to lambda mu2 of so identity I3 tensor theta compose identity I3 tensor theta prime mu2 prime, which is exactly this part like that, which is non-zero by duality as before. By duality. Okay. And we are done. We proved that this is non-zero. So, where is it? We prove this is non-zero, so this is non-zero, which is exactly what we wanted to prove under this one of these three assumptions. So one of these three, each of these assumptions force this F symbol to be non-zero. Okay, so it's technical. The proof is straightforward but technical. Okay. So this trick will be very useful. Now, in fact, the proof of the zero spectrum criterion and one spectrum criterion are almost done. The hard part, or the technical part, the long part, was only this one-dimensional trick. And I am wondering whether we can have other application of that, because it looks very, very interesting, very useful. So now we can state and prove the criterion used to exclude our last fusion ring for the classification. So theorem. So zero spectrum criterion. So for a fusion ring R, so the statement will be a bit technical, in fact. this statement will only involve the fusion coefficient. So we will write something about the fusion coefficient, which is a little bit technical, but in fact, this will be exactly the reformulation of something like xy equals 0. I don't remember, xy equals 0, with x and y different from 0. This will be exactly the reformulation of the existence of a Pentagon equation of this form. And we will explain in the proof why. So for a fusion ring, if there exist indices ij in I for j between 1 and 9, such that the fusion coefficient so n I4, I1, I6, n I5, I4, I2, n I5, I6, I3, n I7, I9, I1, n I2, I7, I8, and finally n I8, I9, I3 are non-zero. It's not finished. So you consider this. You consider 9 indices such that these 6 fusion coefficients are non-zero, together with the following statement, following assumption, and if the following condition hold, so you have four conditions. First one, the sum n I4, I7, k, sum I5 star, I8, I. That's why maybe I use I6, I9 star, k, equals 0. So this should correspond to some Hom space, 0-dimensional. In fact, in the proof, that will prove that the spectrum is of cardinal 0. So the right-hand side of the Pentagon equation is 0. It is exactly the meaning of that. Second condition, n I2, I1, I3 equal 1. This means that the left-hand side, there is only one summand on the left-hand side, and 2 conditions corresponding to the previous lemma, sum over k n k equal 1. So let me write it like that, then I can copy and paste, and I will fill the indices. That or that. And again, something like that. I will fill in the indices. 18. Okay, so what kind of indices we have? I5, I4, I3, I1 star, I2, I4 star, I3, I6 star, I3 star, I2, I6, I1 star. So you have these three conditions corresponding to the previous lemma, and also same for the 18. So here is I2, I7, I3, I9 star, I8, I7 star, I3, I1 star, I2 star, I8, I1, I9 star. Okay. Allô? Allô, allô? On m'entend? Décalage. Décalage? Allô? Il y a un décalage. De combien? Okay, so there may be a little shift between what I am saying and what you are hearing. But anyway. So, if you have these assumptions on the fusion coefficient, and in fact, this kind of assumption can be realized for a fusion ring, but not for a fusion category. So it's a categorification criterion that's really interesting, and R cannot be categorified. This is really the kind of thing we want. A condition which is only on the fusion coefficient, which is very easy to compute. Categorified. And here, in fact, we mean that it is not the Grothendieck ring of the fusion category. So this is exactly what we mean by categorify. Of course, as I said, you can sometimes categorify with a fusion ring may be categorified into a tensor category, which is not a fusion category. If so, it is categorified, but not as a fusion category. In this work, in this course, by categorified mean as a fusion category. So meaning it is not the Grothendieck ring of a fusion category. Of a fusion category. And what is really interesting in this theorem is that it's true for any field, which is quite surprising, quite nice. What we proved before, for example, involving the quantum Fourier analysis, it was for case, so over the what we proved before for localization strategy, I guess it was over the complex field also. Here, it is over any field. And as I said, there are examples of fusion rings satisfying this assumption. So this is nice. Okay. So we will not, I don't know if we will have time to prove that. I will start the proof and maybe finish it tomorrow. It's not so long, but it remains only 7 minutes. So proof. So assume that C is a categorification of R. By assumption, so given that the fusion coefficient are non-zero, so this one, so I will rewrite it because we need to consider the corresponding home space are non-zero. We can select non-zero morphism in the corresponding home space. We can select non-zero morphism. So the corresponding home space are non-zero dimensional, so you can find non-zero morphism inside. Mu1 to mu6 in the corresponding home space. Home space of C. So corresponding, I mean, the home space here, I don't know, from xi4 tensor xi1 to xi6, etc., etc. So, okay. Okay. So now we will consider the equation 15. We will say that this corresponds to empty spectrum of some Pentagon equation. So according to 15, the spectrum as defined before of the Pentagon equation 14, so I will copy and paste again this Pentagon equation here because it's to understand, is empty. So let me copy and paste. So where is it? 14, 14, 14, here. Fact, oh. I guess there is enough room. I hope. Single line. Yeah. Okay. So this is 14. So we already mentioned, copy it several times. Okay. So remember the definition of so the spectrum is empty. The spectrum, it was defined here. So remember, spectrum. So maybe I should copy that also. This is a spectrum corresponding to, and in fact, yeah. IS. Okay, so this is a definition of the spectrum of this Pentagon equation, of this specific equation. And equation 15 say that for all k, this is 0. But this is a sum of non-negative thing. So if a sum of non-negative thing is 0, then every summand is 0. So, but then one of them should be 0. So for all k, for all I, so we don't have this assumption because we know that for all I there is so there one of this is 0. So we have that this is empty. Okay. And yeah, and we will finish tomorrow because it's time. So let me just, yeah, as I said, so you have something empty. So you have a Pentagon equation. So I don't remember the left. This is empty. So this sum is empty here. So this is 0. This is 0. And here, by this assumption, you have only one component, one summand. So you have one summand, and then it remains these two things. We force these two things to be non-zero by the previous lemma, using this assumption and this assumption. Force this and this to be non-zero. So you have x, y, non-zero equal to something equal 0. So, contradiction. And so, this assumption, which is possible for a fusion ring, is impossible for a fusion category. But we will finish the proof tomorrow. So, end of session. Okay, can stop.